Good morning. I apologize if I sound a little bit weird today. My nose is badly stuffed up. I've got some sort of weird cold. But in just a few minutes here, we'll get started. I was a little late posting that link, so as folks trickle in, we will get rolling. There's not a whole lot more to do, but I do want to make sure that we're comfy with what we're doing. So let's get QCam up and screen share going. So today I want to talk to you about the substitution rule. It's the last big hurdle to clear in this class. I want to make sure we have enough time, so I don't want to wait till Friday to introduce it. I think that would be a big mistake.
Good morning, sir.
Good morning.
How are you?
I'm doing well, Tanji. How are you?
Cool. Okay. Can you explain to me a homework test number 22 and 1?
We can take a quick look at those.
Okay.
So did you want numbers 22 and 21 or 22 and 1? This guy, this is good. So 21 is about using properties of the integral. You're going to split this.
It's not 21, number 1 and number 22.
Oh, okay, okay, 22 and 1. All right. All right, so for 22, we should graph the piecewise function. All right, so you've got this piecewise function over here. That's the guy that we're integrating. So if x is less than 5, and I'm sorry that the pen kind of ran there. If x is less than 5, this thing is the constant function 5. If x is bigger than 5, this is the linear function x. Okay. So for x is less than 5, this is the constant function 5, and it would continue over here like this. And if x is bigger than 5, it acts like the linear function f of x equals x, so that's like this. So this is my guy. And they want us to find the integral from 0 to 9. So mark this as 9. So the integral from 0 to 9 is all this area. So I would think of this, this as a geometric area problem. I would think of it like I can find the area of this rectangular region here. Got this triangle plus this rectangle. Let's find the rectangle area. All right, the graph of my function is still just this and this. I want to be clear about that. That's the important thing, right? To get started, you have to be able to draw the graph. So the graph is the very thick black line here that makes this turn. Right here, this point, it's filled in, and this is the piecewise function. But we have to find these areas. So we can split it up into a triangle and a rectangle. The rectangle has a width 9 and a height 5. And then this triangle has a base here of 4, because that's the distance between 5 and 9. And a height here, well, we have to figure out what this point is. But this is f of x equals x, so the point is 9, 9. So that's 5 up to 9, so that's also 4. So that's how it shakes out. 9 times 5, 45. And this is 8. So it should be 53 altogether.
So is it 9.9 or 9? So if you replace a 9 in the function s, it should give 9.
I'm sorry?
I said where you note 9.9, you said that the height is 9.9. So is it 9.9 or 9?
9, 9. So that's an ordered.
Okay, the coordinate, the point. Okay.
Yeah, yeah. This is an x. This is a y. All right. Yeah. So this is a good problem. I'm happy to go over this. This is one of those integral problems where we're meant to solve it geometrically, because this is coming from before we had the fundamental theorem of calculus. Now you could do this these days with the fundamental theorem of calculus. You could integrate up to 5, this constant function, and then you could integrate from 5 to 9, this guy. And in each of those, this piece, the integral from 0 to 5, would just be of the function 5, because f of x there is equal to 5. And this piece from 5 to 9, I would be integrating the function x, because if x is bigger than 5, f of x is x. And we know how to do these now. Now that we have FTC2, we could find an antiderivative. Like that. I'll let you do this. This is not what the problem intends for you to do, though. The problem intends for you to do this. So that's 22. The other one we wanted to look at was number 1. So here we just want to draw some rectangles. 1 over x from 1 to 2. estimate using R4. So that is a Riemann sum, a right-hand Riemann sum with n equals 4. I think that's what they wanted, right? Right-hand sums. What the hell? Where did it go? Did it close? Did it close it? Four rectangles, right endpoints. Yeah, okay. So we draw the graph. This is 1 over x. This is the point 1, comma 1. And here's the point 2, comma 1/2. So the area that I'm trying to approximate is the area in here. And I need to chop this up into 4 rectangles. Whose heights are determined by the y value at their right-hand side. So these are my 4 approximating rectangles. Delta x is always b minus a over n, which is 2 minus 1 over 4, which is 1/4. I know that x0 is here, x1 here, x2, x3, and x4. x0 is 1. x1 is 1 plus 1/4, which is 5/4. x2, I don't really have space here, is 3/2, right? 1 and 1/2. x3 is 3/2 plus 1/4, or 1 plus 1, 2, 3/4, which is 1 is 4/4, 7/4. And x4 is 2. So my Riemann sum, R4, is the sum from I equals 1 to 4, f of xi times delta x. That's f of x1 times delta x plus f of x2 times delta x plus f of x3 times delta x plus f of x4 times delta x. Delta x is 1/4. x1, x2, x3, and x4 are these guys. Sorry, this is x0, yeah. So what we really need are the heights, f of those things. And f of x is 1 over x. So it was x1, it was 5/4. So this is 1 over 5/4 times delta x, which is 1/4, plus x2 is 3/2. This is 1 over 3/2 times 1/4, plus x3 was 7/4. So this is 1 over 7/4 times 1/4, plus x4 is 2. So this is 1 over 2 times 1/4. And then from here, you just have to simplify. You can factor the 1/4. And then 1 over 5/4 is 4/5, plus 1 over 3/2 is 2/3, plus 1 over 7/4 is 4/7, and 1/2 is 1/2. So from here, you would have to have a common denominator. I don't want to burn class time on that, but this is how we would solve this. So we're going to just come up with the Riemann sum. The 1/5, that's this height. Because the graph I'm on is 1/x, and the x value there is 5/4. The 1/3 is this height, because x2 is 3/2, and I'm on the graph 1/x. The 1/7/4 is this height, and the 1/2 is this height. You can even see it right here. And then delta x is the width. The width of each of these is 1/4. So that's why each one is being multiplied by 1/4. So it's a Riemann sum problem. And then from here, like I said, you would have a common denominator, and that would do it. So I do want to spend the majority of the class time today on learning the substitution rule. So let's begin section 5.5. We all remember what a headache it was to learn the chain rule, right? Well, the substitution rule, it's a backwards chain rule. That's what it is. The basic idea is this. If you're trying to find an antiderivative for a composite function, and you're able to recognize his derivative also floating around in the integral, then you can see this as looking like something that came from a chain rule differentiation, right? A chain rule derivative. I want to write it how your book writes it. I don't want to make this any more confusing than it needs to be. So they use a G. F of U, okay. They're saying if U is G of X differentiable in the interval I, then, yeah, that's not really helpful, is it? So let me come back here. This we can think of as the integral of F of U du. That's the idea. So in other words, this piece is like du, and this piece is F of U. So you can make a change of variables. In other words, this is a we can change the variables in an integral by substituting as long as we account for the differential. So let me show you what I mean. I think learning this by example is the best way to go. So the formula is here. If I want to integrate something like 2x times the square root of x squared plus 1. First, observe that because the square root is like a grouping symbol, I can't distribute the square root over this. The square root of x squared plus 1 is not equal to x plus 1. We can't do that. That's something that people often want to do when they see this. But you have to remember that square roots never distribute over addition or subtraction. They distribute nicely over multiplication and division, but the square root and powers in general do not play nice with addition or subtraction. You'd have to do something like foiling out the square root, which is not doable, at least not without power series. So how do we integrate this? how do we get this into a form where we can see an antiderivative? Well, I'll tell you what I see. If this was just the square root of x, then this would be easy. If not for this plus in here and this 1, this would be easy because the square root of x squared, that is x, or at least the absolute value of x. And then I would be able to integrate that using my power rule. Another thing I see is that the derivative of the stuff underneath the square root, the derivative of x squared plus 1 is 2x. So this kind of looks like this, doesn't it? I can rewrite this as the integral of the square root of x squared plus 1 times 2x dx. And then this piece looks like f of u. This piece looks like u primed. So here's how we do it. I make the substitution. U equals x squared plus 1. And when I do that, I need to calculate du, which is 2x dx. And then I say, okay, here, and this is just a note, so let's get this off to the side. So that under this substitution, my integral, the integral of square root x squared plus 1 times 2x dx, this is now going to be the square root of u, because x squared plus 1 is u. And 2x dx, that's exactly du. So everybody see what happened there? I'm thinking especially how we calculated this.
How would we know which part to substitute u out for in the standard integral?
That's the challenge. So one of the reasons this is a difficult section is because there's an element of creativity. You have to choose what you want to substitute for, and it's not always obvious. This particular example is nice and straightforward, and what I look for is an inner function whose derivative is floating around somewhere else in the integral. So I see here x squared plus 1 kind of inside another function, like inside the square root. And I think, oh, okay, so what's the derivative of x squared plus 1? It's 2x. Do I also have that? And the answer here is yes, yes I do. So that tells me that that's a good substitution to try.
All right, I got it. Thank you.
Make sense? Okay, now from here, this is easy. This is now the integral of u to the 1/2 du. So that's a power rule thing. Integral of u to the 1/2 is u to the 3/2 divided by 3/2 plus c, which is 2u to the 3/2 over 3 plus c. And then my last step is to go back to my x's. So that's 2 times x squared plus 1 to the 3/2 over 3 plus c. So this is how these problems go. So you're looking for, you look at your integrand, the thing you're integrating is called your integrand, and you try to spot an inner function whose derivative, or at least something like his derivative, is floating around. So here's my inner function, and I go, oh yeah, that looks a lot like his derivative. Then I usually shuffle this piece over to sit next to the dx, and then I try the substitution. So I calculate, okay, u is going to be x squared plus 1. That means du is going to be 2x dx. And the way we do that, I wrote down here in case you didn't see it. You take du over dx, the regular derivative, du dx, and you multiply both sides by dx. But usually we just write it straight up like this. So you take the derivative over here, and then you slap on a dx. And that is your du. Then you try to plug everything in. This is one of the reasons it's so important that you always write your dx's, because this whole piece, 2x dx, that is du, right? 2x dx is du. And then the square root of x squared plus 1 is the square root of u, because u is x squared plus 1. And then once you have everything in terms of your new integral, or in terms of your new variable, you've got your original guy replaced, you've got your differential replaced, then you can step back and ask yourself, okay, is this integral easier than the one I started with? And the answer here is yeah, hell yeah, because I know how to do this one. I just rewrite that as a 1/2 power, and then I use my power rule. Does that make sense? Ways to spot when to use substitution. This looks like the result of a chain rule thing, right? Again, because the derivative of the inside is sitting outside. This looks like something that would happen when you differentiate something with the chain rule. So that's a good way to identify whether or not you should try the substitution. There's lots and lots of examples. Are there, and most of them are harder than this. So are there any other questions, anything that feels weird here that we would like to talk about a little bit more before I pluck out a tougher one? Okay. An integral we haven't been able to do so far is the tangent function. I'm going to write this in terms of theta just to try and get us used to using different variables. Here, I don't see an obvious inner and outer. I don't see anything floating around that I could group with d theta. But if I write tangent as sine over cosine, I start to see something. The derivative of sine is cosine, and the derivative of cosine is negative sine. So I start thinking, well, I can't get the cosine out of the bottom, but I can pull the sine off of the top. So if I think of this as my like outer with this inner, then the derivative of this inner, not exactly, but very close to the derivative of this inner, is sitting right here. So let's try the substitution u equals cos x, or sorry, cos theta. Then du d theta would be negative sine theta. So du is negative sine theta d theta. And if you multiply both sides by -1, you get -1 times du is equal to sine theta d theta. So here's my sine theta d theta. That will be -1 times du. And then 1 over cos theta, that will be 1 over u. So there's some natural log stuff going on here. This will become 1 over u times -1 du. And then this -1 is a constant multiple. So he can come out front. Like this. And now 1 over u du, that's natural log, right? The integral of 1 over u du is the natural log of the absolute value of u. And we add on our plus c. And then we substitute back in for u. What was u? U was cos theta. So the integral of the tangent function is a little bit complicated. It's the negative natural log of the absolute value of cos theta. Cool stuff, right? Questions about any of these steps? I'd like you to take your time and make sure you really understand every single step. Okay. Let's try a couple more. What about the sine of 10t dt? Here, it's the 10 that's causing problems. My outer function is like sine, my inner function is this 10t. So I want to let u be 10t. du is then 10 dt. But I don't have a 10 dt floating around inside my integral to use. So here's the first problem we've seen where the p need for the differential is not sitting in here, right? I don't have a 10 anywhere except in here, but this is trapped inside my sine function. So I certainly can't use this. This is what I'm substituting for. But there's a way to handle this. Different ways people think about this. One of them is to solve for dt. If I solve for dt, I can try just plugging in. So this is the same as saying 1/10 du is equal to dt. So in place of dt, I can write 1/10 du. Another way to do it is to multiply and divide by 10 in here. And then the 10 that's upstairs stays with the dt to be replaced by du, and the 10 that's downstairs pops out front. But for now, I'll just do it like this. We'll just plug in 1/10 du for dt. So this will be sine of u times 1/10 du. I think most people, when they first learn this, prefer to do it like I'm saying here. So if you're having a hard time finding like the sine theta d theta piece that we used here, if you're having a hard time finding the differential piece that you need, you can always solve for the original differential and then plug in. So here my original differential is dt. I need to replace that by some du stuff. And the easiest way to do that is to just take this equation and solve it for dt. And then plug that in. So dt is 1/10 du. So where there was a dt before, there will now be a 1/10 du. And now just like the -1 from the last guy, this 1/10, he can pop out. And the integral of sine u du, who differentiates to sine? Not cosine, but negative cosine. So this will be negative 1/10 cos u plus c. And then my last step is to go back to the original variable, which was t. So u is 10t. And all the integrals that kind of look like this, sine or cosine of some number times t or some number times x, they're all done this way. So like cosine of 50x, you would substitute u equals 50x. So these are some indefinite integrals done with substitution. We can do maybe one more like this, and then I'm going to show you some definite integrals. Questions on these examples before I move away from them? Is it clear what we're doing and why we're doing it? In each of these problems, I'm looking at them and asking, what's making this hard, right? Here, what's making this hard is the 10. I know an antiderivative for sine. If it was just sine, like sine x or sine t or whatever, that would be easy. But I don't know an antiderivative for sine of 10x or sine of 10t. So my goal is to get rid of the piece that's making it hard. So if I realize, oh, well, if I substitute for this, then that piece that's making it hard goes away. Oh shit, yeah, I can do this. Similar thing here, right? I know how to integrate 1 over x. The thing that's making it hard is the cosine. So if I substitute for the cosine, then I would have something I know how to integrate. Oh shit, yeah, I know how to do this. And luckily, we have the extra piece that we need to make the substitution work. So mistakes that people make here are forgetting to do something with the differential. This is why it's so important that you always write your dx's or your d thetas. Never get in the habit of writing integrals without those. They're so, so important. All right. Let's try something a little harder. Let's try and then let's try this. This is not as easy to spot. Definitely the large power down here looks scary. I'd like to get rid of that, or at least reduce that if I can. I don't have any tools for integrating things like this really. But when I look at this, I see something that kind of looks like, oh, well, if this was a 1 and this was an x squared, then 1 over 1 plus x squared, I know that that integral is arctan. So this is kind of in the shape of the derivative of arctan, but it definitely doesn't look like it yet. So I'm going to start trying to massage this until it looks more and more like an arctan integral, just because it has that shape, something over 1 plus something. Why not? Let's try it. So my first step would be to pluck that x squared off. Okay, so there's 1 over 1 plus something. And remember, arctan is 1 over 1 plus x squared. But this doesn't look like that. Can I write this as the square of anything, though? Yeah, x to the 6 is x cubed all squared. Oh, shit, and this is pretty much the derivative of x cubed. So one more little rewrite. And we're on our way. So from here, I can tell what to do. This is my outer function. This is my inner function. This isn't exactly the derivative of my inner function, but it's pretty close. The derivative of x cubed is 3x squared. So we're going to try to substitute for x cubed and try to make this piece work with the differential. So I'm going to let u be x cubed. Then du is 3x squared dx. And again, if it's not super obvious how you should make use of this, you can solve it for dx. That'll be 1 over 3x squared du. So what do I get? Integral 1 over 1 plus x cubed is u. So this is u squared. And then this, I've got x squared times dx is 1 over 3x squared du. Now what I've done here is a little bit naughty, and I want to be clear about that. I'm going to put this in quote bunnies. That's my, I'm not responsible for this shit symbol. This is naughty. I cannot do any integrals that have two different variables in them. So before we're able to move to an antiderivative step, we need to make sure that there aren't any more x's. The x's are not constants. They cannot be popped out of the integral, but they're also the old variable. They're not the new variables. So my new stuff has to have just u's. And when we write down a step like this, it's usually just to help us see how things are going to play out. But if the x's don't all cancel perfectly and go away, you got to erase it all and go back and try something else. Now here we get lucky. This x squared cancels with this x squared. And I get integral 1 over 1 plus u squared times 1/3 du. And if you're really clever, you can see that that's how it's going to play out from the start. You go, oh, x squared dx, that's 1/3 du. And that's what we usually like to do in Calc 2. But it's not at all uncommon in Calc 1 to have a kind of in-between step like this to help you see where it's going to go. You just need to remember that this business here where you've got an integral that's got two different variables in it, like u's and x's, kind of not okay, kind of bad. So before you move on from this step, you need to make sure you get rid of all the old variables. There can be none of the old variables anywhere, not in the differential, not in the function, not anywhere when you do your integration step. But here we got lucky, all the x's were able to cancel, and we could have seen that before if we were a little bit more forward looking. And we get to this, which just has constants and u's and du's, no x's or dx's. So I'll shuffle my constant out of the integral, and I get integral of 1 over 1 plus u squared du, and this guy I know what to do with. That's arctan. So I get 1/3 times the inverse tangent of u plus c. And then my last thing here is going to be to go back to my x's. U is x cubed. An important comment. You can always check your work with an integral. You can always differentiate this thing and see if you get the thing you started with. If you're ever unsure, oh, did I fuck up somewhere in there? Is this not okay? You can always check by differentiating. So if I'm worried that maybe I made a mistake, I can differentiate this and see what I get. The plus c will differentiate to 0, and I'll get 1/3 times the derivative of arctan is 1 over 1 plus the inside squared, so that's x cubed all squared. And then we multiply using the chain rule by the derivative of the inside, which is 3x squared. So the 3 and the 1/3, 1 over 1 plus x cubed squared is x to the 6. Cancel. And we do get x squared over 1 plus x to the 6. So we're good. Because that's what I was integrating to begin with. So if you ever have any doubt, check your work. It's a good way to practice your differentiation skills, and it's a good way to reassure yourself that you did everything right. Integration goes really deep. This is not like differentiation. You guys have learned all that you ever need to learn about how to differentiate functions, but you could spend the rest of your lives studying integration and still not know enough. For some reason, going the other direction in the differentiation chain is much, much harder. There are mathematicians whose whole job is to research integration methods. In the first half of Calc 2, you're going to learn a shitload of integration methods. You're going to learn integration by parts, partial fractions, a whole bunch of different tricks for integrating all sorts of functions. It's hard. So checking your work is wise. When it comes to substitutions, this business where you like solve for the original differential and then plug in and hope everything cancels is okay. But you want to start evolving towards going from this step to this step, because this step causes trouble. Leonard, did you have a question there, buddy? You're getting some mic noise, so if you don't have a question, I'm going to go ahead and mute you, but feel free to unmute yourself if you do have a question. Okay, so our answer here is this, and we're able to check our work by differentiating. And this is a sneaky substitution problem, right? This one's not obvious. So spotting what to substitute here, I think, is quite tough, at least until you get to this line. If I handed you the integral as it is in this line, I would expect you to be able to see it. But it's not super obvious to go from here to here. But what I'd like to do now is show you how to substitute in a definite integral. I see there's a comment or something in chat here. Let's take a look at that. There will be a meaningful amount of integration on the final, yeah. I would be doing a disservice to not put some on there. So what can we try next? What would be fun? How about this? Oh yeah, sorry. Yeah, we can stay here just a second longer. So I left the 1/3 out front alone. I differentiate arctan of stuff to 1 over 1 plus that stuff squared. And then I multiply by the derivative of the inside stuff according to the chain rule, and the derivative of x cubed is 3x squared. And then in this line, I shuffled the 3 out front with the 1/3 because these are all being multiplied. I can do that in whatever order I want. I put the x squared over here, and x cubed raised to the 2 is x to the 3 times 2 is x to the 6. So in this line, I just rewrote x cubed squared as x to the 6, and I shuffled this 3 out front. And then in the last line, x squared times 1 over 1 plus x to the 6 is the same as x squared over 1 plus x to the 6, which was my original function. Okay. So let's then move to this guy. And maybe in order to make this a little simpler, I'll just, instead of ln2, I'll let my upper bound just be 2. We'll modify that just a little bit. I want us to be able to see where things are coming from and not be overwhelmed. So this function is x times e to the negative x squared. Only now it's a definite integral running from 0 to 2. So we're not just finding an antiderivative here, we're actually finding an area. And one of the important things to remember is that with a definite integral, if you're going to make a substitution, you must change the bounds. These bounds are for x. This is x equals 0 up to x equals 2. I'm going to substitute in something for u. And I need to figure out when x is 0, what is u? And that will be my new lower bound. When x is 2, what is u? That will be my new upper bound. And just like before, I kind of look at the big function and I ask what makes it hard. If it was just e to the x, this would be easy. So this is the piece that I kind of want to complain about. This is the piece that I want to get rid of. And conveniently, his derivative, or something very similar to it, is sitting right here. So I'll rewrite this as the integral from 0 to 2 e to the negative x squared times x dx. And now here's the substitution. The thing that's making this hard is definitely the negative x squared there. If it was just e to the x or e to the u, I would be happy. So let's make that u equal to negative x squared. Then du is negative 2x dx, which is not exactly what I have here, but it's a constant multiple of it. So I can say, okay, negative 1/2 du, that's x dx. So x dx, that's what I've got here. That's equal to negative 1/2 du. So I'll be plugging that in. Also, I need to change my bounds because this is a definite integral. So when x is equal to 0, u is equal to negative 0 squared, which is still 0. And when x is equal to 2, u is equal to negative 2 squared, which is negative 4. So this is all the stuff I need for my substitution. Here's all the things we've been doing, like in an indefinite integral. But then I also need this work to change the bounds. Very, very important that you change the bounds. Because these old bounds are for x. And I'm changing my whole integral to be an integral in terms of the variable u. So under this substitution, my integral becomes the integral from 0 to -4, right? 0 stayed 0, but 2 became -4. E to the -x squared, that becomes e to the u, and x dx is -1/2 du. And I encourage you to write parentheses like that. It'll help you to remember that this is being multiplied, right? This is times x dx, and x dx is -1/2 du. Now I can shuffle this constant multiple out front the integral. And what's left is very easy to integrate, e to the u du. There are some things I could do. Like I could take this negative right here and use it to flip these bounds, which is kind of appealing because I like the number up here to be larger than the number down here, and right now it's not. So some people would do this. You don't have to do it. You could leave the negative and the bounds as they were. But since we're learning about this stuff now, it's good to show you. So I'm using the negative here to flip these bounds over. Negative integral b to a is the same as the integral a to b. And now there's really nothing more I can do to clean this up. I just need to find an antiderivative. So this is 1/2 times, an antiderivative for e to the u is e to the u. And I evaluate that from -4 to 0. The good news about definite integrals, integrals with bounds, when you make a substitution like this, you don't need to go back to the old variables. You just need to evaluate between these new bounds. So there's no need to plug back in for u in a definite integral. In an indefinite integral, you have to plug back in. In a definite integral, you just have to evaluate between these new bounds. So this is 1/2 e to the 0 minus e to the -4, which is 1/2 1 minus 1 over e to the 4. And there's no plus c, again, because this is a definite integral. The answer is just a number. It's this number. So I'd like to try a few more definite integrals that we do by substitution. First, questions on this one. I'll leave this up for just a second longer. Anybody who's writing? This is my normal substitution and differential work. Here I solved for x dx because that's what I had floating in my integral. And this is kind of doing something like this is sort of halfway between that mixing variable stuff that you shouldn't do. Here I don't end up mixing any variables because I didn't solve for dx. We always do it in that order. So it's always plug this in, then subtract what you get when you plug this in. Always upper minus lower. So Angelica in chat asks, how do we know that it's in this order? E to the 0 minus e to the -4 and not the other order? And that's always the case. So that evaluation thing is always capital F of B minus capital F of A. I took this negative here and used it to swap the -4 and the 0. We could have not done that, and this would just be negative, and then these would be in the opposite order. And then when you distribute the negative, it would turn into this. But we always do plug in this and then subtract what you get when you plug in this. Always upper minus lower.
Question for you.
Say that again, Sergio?
Yeah, question for you. So in the first part, the 1/2 and the bracket E, no, down, all the way down.
Yeah.
Yeah, right there. To the fourth, when we go, before that step actually. Yeah, right there. Do we just ignore that 4 there and then plug it in how you did in the next one?
Ignore
If that makes any sense.
4?
No, the one inside.
So this is a U.
That's a U. That makes a lot more sense. My apologies. Thank you.
No, you're good. Yeah, that's the variable U. Yep. Yeah, sorry about that. Other questions on this fella? So a fun fact, e to the negative x squared without this x here is impossible to integrate. There is no closed form antiderivative. It's not just that it's hard and we haven't found it yet. It's been proven that there is no closed form antiderivative for e to the negative x squared on its own. So we need this x in order to do this integral. Okay. Let's try a couple more of these definite integrals. What would be a fun one? What haven't we done yet? Classic sort of U sub problems. Maybe I'll look in your book, see if they got something there that I haven't thought of lately. Yeah, everybody does those. Yeah. Oh yeah. This is fun. So the truth of the matter is we don't know how to integrate natural log x. We've never seen the integral of this. We know that the derivative of natural log x is 1/x, but we don't know how to integrate ln x on its own. And you won't actually learn how to do that until Calc 2 because it requires something called integration by parts, which is like a backwards product rule. But this integral can be rewritten as ln x times 1/x dx. And I recognize 1/x as the derivative of ln x. So here, if I let u be ln x, the whole thing, then du is going to be my 1/x dx. And when x is equal to 1, u is equal to the natural log of 1, which is 0. And when x is equal to e, u is equal to the natural log of e, which is 1. So I've got my 1/x dx here, that's du. And what I've got here is just u. So this is the same as the integral from 0 to 1 of u du, which is pretty cool. And now that's a straightforward power rule integral. I add 1 to the power and divide by that new power. And then I evaluate that between bounds. So this would just be 1 squared over 2 minus 0 squared over 2, which is 1/2. This is a fun problem. Another thing that you want to be warmed up for as you come into Calc 2 is dealing with trig functions. A lot of people have a phobia of trig functions, but you will need to banish that fear moving into Calc 2. So let's look at a handful of problems like that. We'll give just a second longer for anybody writing here.
Professor, you're having office hours today, correct?
Yep. Yeah, normal office hour from 1 to 2.
From 1 to 2? Okay, cool. We'll try to make it. I have some questions.
Okay, that sounds like a plan.
Thank you.
Let's see, I think we got time for 1 or 2 more here. Let's go back and do another indefinite integral. Let's integrate sine cubed x times cos squared x dx. Ooh, and then we can do secant. Secant is hard. So this one's fun because it's definitely not obvious at the start what we should do. I can't integrate sine cubed and cos squared on their own. Integrals don't play nice with multiplication anyway. But what I can do is set one copy of sine x over here with the differential. Because the power of sine is odd, when I grab 1 to sit over here, what's left is an even power. And then I can use the Pythagorean trig identity sine squared plus cos squared equals 1 to rewrite the remaining 2 copies of sine in terms of cosine. So if I go 1 step further here and rewrite sine squared as 1 minus cos squared, then I'll be in good shape to make a little substitution. So having done this algebra, or this trig, I guess, can anybody see from this line what a good substitution might be?
U equals 1 minus cosine squared x.
Well, not quite. If I did that, the derivative of 1 minus cosine squared would be negative 2 cos x times sine x. Because and this is the piece I want to use with my differentials. Think simpler, much, much simpler.
Then just the cosine squared x.
Simpler. How about just cos x? Then du is negative sine x dx. So this piece is negative du. And what's left will just be a polynomial. So the goal usually with these sort of sine, cosine, or secant tangent integrals is to turn them into a polynomial. This would be 1 minus u squared. This would be u squared, and this is negative du. If I get greedy and try to substitute for too much, you have to remember that your differentials here, when you calculate your derivative, you would need the chain rule, right? The derivative of cos squared is not just sine. It's 2 cos times negative sine. So if we get greedy and try to substitute for too large a chunk, like 1 minus cos squared or even just cos squared, I actually would not have the pieces I need to make that go. But this is quite nice. I can pop my negative 1 out. And the result is a polynomial. I can distribute this u. And now use the power rule. U squared will become u cubed over 3. U to the 4 will become u to the 5 over 5. And then I'll distribute that negative and also plug back in for cosine. So this is negative cos cubed x over 3 plus cos to the 5x over 5 plus c. Now you could try the substitutions you guys are suggesting. The 1 minus cos squared seems very tempting for a lot of people. But this piece isn't going to be super nice, right? If u is 1 minus cos squared, then what would I do with this? And also the differential of 1 minus cos squared is not just sine x dx, or even a constant multiple of sine x dx. So you're welcome to try those. Just make sure that as you do this, you're very, very careful and you're not doing any illegal algebra. It can be tempting to like force something through when you want it. But make sure each step, you're certain that what you're doing is kosher legal algebra.
How did you change the u squared minus u4 to the u cubed over 3?
Oh, I integrated. So I used the power rule for integrals. So the integral of u squared, or an antiderivative for u squared, I add 1 to the power and then divide by the new power.
Oh, okay, gotcha.
Add
Thank
1, divide by the new power. So this is the step where the integral symbol went away. So that's the step where I took antiderivatives.
So that's integration right there. You add 1 to the top and divide by the exponent.
It only works for things like this. If you have anything more complicated, like any addition or subtraction or more complicated function stuff going on here, it doesn't work. But if you're trying to just straight up integrate a power of x or a power of u, then yeah. Remember this from our antiderivative table. An antiderivative for a power function, you add 1 to the power and divide by that new power. This works for all n except for -1. Because the negative first power of x is 1 over x, and his antiderivative is the natural log.
Okay, beautiful. Thank you so much.
Yeah. Take a look at that antiderivative table in your textbook. It is in the section on indefinite integrals right here. So these are things that we should know, with the exception of this last row. Don't worry about this last row. We haven't talked about hyperbolic trig functions, but all of these are things that we should know.
Okay, beautiful. Thank you.
Yeah, of course. All right, do we have time for one more? There's one more fun problem here while we're talking about trig integrals. This one's gonna feel a little weird, but I gotta show you because it's cool. That's secant, my shitty handwriting, integral. The integral of the secant function. So I have to show this to you because it's one of those like classic finishing problems in Calc 1. But be warned that the first step, nobody would ever think to do. We're gonna multiply by secant plus tangent over secant plus tangent. It's a very strange thing. I'll do it down here. So I'll still have my secant x, and then I multiply by secant x plus tangent x over secant x plus tangent x, which is admittedly a very strange thing to do. But we do it for a good reason. If I then distribute this over the numerator, I get integral secant squared x plus secant x tangent x divided by secant x plus tangent x. dx. Why the hell do we do this? Well, the derivative of the bottom is the top. The derivative of tangent is secant squared. The derivative of secant is secant tangent. So if we substitute u equals the denominator, just like we did when we did the original tangent integral, then du, derivative of secant is secant x tangent x, plus the derivative of tangent is secant squared x. So that's du, which is my numerator. I mean, it's written in the other order, but that doesn't matter. It's addition. You can do it in whatever order you want. So I recognize this as 1 over secant x plus tangent x times secant x tangent x plus secant squared x dx. And now I can plug in that substitution. This piece is 1 over u. And this whole mess here is du. So it's a very, very sneaky substitution. Admittedly, nobody would see this. Nobody would see this coming, at least not the first 10 years they stare at the problem. All right, so everybody following what's going on here? Secant x is the same as secant x over 1. So I multiply these fractions straight across and I get this. Nobody would know why we start by multiplying like this. God just whispers in your ear and says, hey, have you tried multiplying by secant plus tangent over secant plus tangent? And you go, no, let's see what happens. When we do that, we get this. And you stare at this long enough until you realize that if you substitute for the bottom, the differential is the top. So you regroup your fraction. You take 1 over that denominator times that numerator. And then shit, that numerator, that's my differential. So this becomes 1 over u du. It's one of the craziest little substitution problems that's out there. Integral 1 over u du, that's natural log, absolute value u, plus a constant. And then because this is an indefinite integral, I have to go back to my original variable. So that's the integral of secant, the natural log of secant plus tangent. Odd powers of secant in general are hard to integrate. Secant cubed, I would love to show you, but I can't. It's gonna have to wait for Calc 2, because again, requires integration by parts. And that is section 5.5. So many of these problems are not that hard, right? If you think about the ones we started with, they're not bad. But they can get very complicated. You need to be rock solid with your algebra. You need to be making sure that your algebra is flawless. You need to be rock solid with your differentiation, because every substitution requires first taking a derivative to get the differential. So your algebra and your differentiation need to be flawless. From that perspective, these aren't that bad. Angelica asks, am I going to make you do this problem on a test? No, probably not. That would be mean. But there may be problems on a test where it's worthwhile for you to know that the integral of secant is natural log secant plus tangent. And that would be mean also. It's not likely. I wouldn't do that to you in Calc 1. But in Calc 2, you can expect this and far worse. So a good test caliber question. It's a worthwhile comment. A question about the level of difficulty you could expect on a test. These guys. These would be good test level questions for Calc 1. So something like either of these could show up on the final or in exam 3. That would be fair. But this last example here, this is definitely just fun challenging stuff. All right. This one at the bottom here would also be a good test level question. So that's substitution. None of it is out of control hard. But you do need to have like perfect algebra and differentiation skills to get good at this. So the homework from this this week is going to have a meaningful amount of your study guide, right? Homework 11/study guide 3 has a little bit of this stuff. We can real quick make a few comments on that, and then we got to get going. Oh, that's Calc 2. So. Here, right? Like cos 8x, that's like sine 10t. So you substitute for the inside, that's not bad. This is kind of similar to one of the ones we did. You substitute for the thing under the radical and hope that you have the piece out here that you need to make it go. Some of these, I don't tell you what to substitute for, like in this one, but this looks a lot like this. So you probably want to try the same thing. You probably want to try substituting for whatever is under the radical and see if you can make it go. Same business here, only it's a definite integral. This is kind of like the e to the negative x squared integral we did. So the thing that makes this hard is the 1 over x to the 4. So I would try substituting for that. So that's where I'm going to leave it for today. Please continue working on that homework. Remember, homework 11 is also study guide 3. So as you go through those problems, you need to be writing out solutions, nice, neat, careful solutions. And if you run into any that you want me to critique or give you some feedback on, send them to me in an email or Canvas message, and I'd be happy to do that. Also, I have an office hour this afternoon from 1 to 2. So if you want to pop by and ask some questions there, we can do that as well, okay? All right, I gotta sign out. I will see you guys either in office hours or on Friday.
Thank you so much.